starting, this is lecture number 9, I guess. Thank you for reminding me to record it. And we are starting by answering a question here, which you can read. You can actually, I just read it, so I'm not going to say it again, but if you want, you can pause it to read it. But the question says, find the percent of scores greater than 28. Well, so I'm going to annotate this a little bit so you can see what I'm referring to. How many scores are greater than 28? That many. How many were there altogether? That many. So you just do this divided by this, and the answer should be 10.68%. It's not asking for anything in terms of the normal curve here. It just specifically wants what percent were greater than 28. That many were greater than 28, that many total. This divided by that is your answer. For greater than or equal to 28, same thing, but now we're going to include this. So these two numbers added together is the top, and we're still dividing by this number. And of course, the percentage has to go up, it can't go down. Now it's 13.83%. Does that make sense so far? No normal curve situation yet. All we're doing so far is just what does the data actually give us? Now, find the percent of observations that are greater than 28 using an n of 21 5.5. So to that end, let's go to crunch it. How do I go to crunch it? I guess I have to stop sharing for a second. And then, is there a way to get crunch it in the problem? Well, let's remember what it said. I'll share again for a quick sec. So annoying. So let's just see. Okay, we're looking for greater than 28 for a 21 5.5 distribution. Can someone just make sure you remember that? Because when I leave this screen, I'm not going to have it in front of me. And their answer they're claiming is 10.2%. So hopefully we'll get the same thing. So we want greater than 28 for a 21 5.5 normal. So let's go now to crunch it. And okay, so let's load up crunch it. So now I'll start sharing again now that I'm on crunch it. Okay, so we're going to go to normal. What's the mean?
21.
21. What's sigma? Was that 5.5?
Yeah.
5.5.
And we want greater than 28. And what was their answer? 10.2%. Well, according to this, unless I get the numbers wrong, was it 28? Oh yeah, no, it is 10.2%. They rounded. 0.102, 10.2%. So does that make sense for that one? I hope it makes sense. When you guys watch these videos after, those who do you see all the text messages with it or just the video?
Like the messages they send in the chat, or?
Yeah. Do you see that with the video? Just the video?
So far I haven't been.
Okay, that's good. That's good because these are, some of them are private messages, and I didn't know if you saw them or not. Okay, so we were on PowerPoint 4/5. We had finished the section 4 portion of the PowerPoint, and we were on the section 5 portion of the PowerPoint. So let's see where we are. Again, I have no idea where we left off. So anyone recall what slide that was?
We're like around 32.
32, regression warnings. All right, good. Okay, regression warnings, slide 32. So let's all go to slide 32, please, so we can talk about regression warnings. Isn't that exciting? So what are the regression warnings? What are the things that you have to be concerned about when doing a regression analysis? So one, and I mentioned this last time, the sample correlation only measures linear association. So even if there is some kind of connection between the variables, but it's not linear, then your sample correlation value will be, it'll give you, you can't interpret it. I mean, I don't know what you'll get in terms of the number between -1 and 1, but you can't interpret it meaningfully unless you have a linear relationship, okay? There are ways of taking data which is not linear and making it linear. There's certainly ways of doing that, but we're not going to worry about that in this class, I don't think. If you've ever taken a science lab, a physics lab, or chemistry lab, has anyone here ever had a situation where you had to take data which was not linear and linearize it in order to calculate a variable, a constant, proportionality or something? Yes, so at least one person has. It's done in chemistry a lot, it's done in physics a lot. Lots of relationships are not linear, but you can change your X and Y values and make it linear. In chemistry, for example, have you guys done a lot of this is science majors, right? So you've probably all done chemistry. Have you guys studied integrated rate laws in reaction dynamics in chemistry? Yeah, so remember, when you're solving the integrated rate laws, you either do a natural log curve or a 1/x curve and stuff like that to see the linear. Yeah, 3 types: first order, 0th order, and second orders, right? So one order is already linear, but the other 2 are not, so you linearize them. Anyways, I'm just giving an example. If you haven't done chemistry or you don't know what I'm talking about, don't worry about it. Anyways, number 2, regression line uses X to predict Y only. The regression line is only used to predict the Y variable when the X variable is known. If you want to use Y to predict X, then you got to start over again. Okay? You got to basically just start over from complete and utter scratch. We don't use Y to predict X. We use X to predict Y. If it was the other way around, we'd have completely different equations, and we just don't do it. So don't try to say, oh, yeah, I'll just switch it around. Start over. 3, this is the big one. The big one that people, well, actually, there's all 4 of these are big ones. That's why they're in big, bold, red type. But the next one is called extrapolation. Okay? Suppose I did a study of heights of children versus their age between when they're born and when they're, let's say, 1 year old. How would it look, the heights of children versus age from 0 to 1? What would the general shape be, do you think, from 0 to 1? Approximately. It doesn't got to be perfect, but what do you think? Would it be positive? Would it be negative? Would it be linear? Would it be nonlinear?
Positive.
Certainly positive. As they get older, they get taller. And I think linear is a pretty good approximation. Does it stay linear forever?
No.
No. If I were to use the data from 0 to 1 to predict how tall an 80-year-old would be, I'd get like 600 feet. Okay? Because in reality, what happens is it peaks up and it kind of tails off, right? You don't keep growing forever. If you try to apply your data, your best fit line, outside of the region of your data, you are extrapolating. You're saying, well, okay, take this data and apply it to a further situation. Sometimes you can, sometimes you can't. Just always be careful about it. If you're too far outside the data, it could make absolutely no sense. It might be applicable. I'm not saying as a general rule it's never applicable, but just be aware when you do something like that, that sometimes you can't rely upon the data. And finally, the last one. Association does not imply causation. Have I given you guys the example of people living longer because they have more cars?
Yeah.
Okay, yes, right? Just because you have more cars does not automatically mean you're going to live longer. There's not a causality relationship. A does not cause B. A is just connected to B. People who have more cars have more money. People with more money have better healthcare, better access to medicine and treatment. People with better healthcare and access to medicine and treatment tend to live longer. They are connected, but one does not cause the other. Statistics can only talk about correlation. Statistics cannot talk about causation. You can't say whether something causes something else from the mathematics. That comes from common sense. That comes from analyzing the situation and thinking about the situation. And sometimes your common sense is wrong. It's not so sensical. Okay, sometimes you think one thing and someone else thinks something else, and you go over it and you realize, oh, their analysis is better than mine. That's fine. Okay, does that make sense though? Yes, so far so good? Okay, so let's look now at the next slide again. Okay, R is a measure for linearity only. We just talked about that a few minutes ago. Okay, correlation requires both variables to be quantitative. You can't do it for categorical variables. You can only do it for quantitative variables. So it makes sense to do the arithmetic in the formula for R, right? There's no math involved in categorical variables, only quantitative. So you cannot use the correlation idea and regression if it's not quantitative. Again, does not describe curve relationships, no matter how strongly. If you do believe that there's a curved relationship, then you change your variables from a curvilinear system to a linear system and start over again from scratch. We're not going to do that. Okay? Correlation is not resistance. Okay? R is strongly affected by a few outliers. Okay? If you have outliers, it will dramatically affect R, to the point where one outlier or one data point can have a humongous effect on everything. I mean, if you think about it, if I gave you the following data, does that appear to be have a linear relationship? Yes,
Yeah.
right?
Yes.
Oh, I forgot one data point. How about now?
No.
Well, it still is, but it went from that to something like this. Right? That one extra observation considerably changed our best fit line and the correlation. We call that an influential observation, one that influences the mathematics. We'll get to that later. But outliers, even one, can have a humongous effect on the situation. And correlation is not a complete summary of two variable data. There's a lot more to it. And as we get through the chapters, we're going to see some of the other stuff. Okay? So let's go to the next slide, unless there's a further question. Okay, so let's look at slide number 34. It says, example, violation of linearity. The scatter plot below shows the amount of time needed to execute a task versus years of experience for a sample of 10 employees. Now, I would think that the more experience you have, the faster you do the same job, correct? As a general rule, that seems reasonable. And therefore, I expect to have a negative relationship. So as the years of experience go up, the execution time goes down. Does that seem like a reasonable expectation?
Yeah.
Okay. And the data points, certainly portray that information. Okay. Even though the relationship is clearly not linear. If you look at the graph, if you ignore that line that they already drew in there, and you decided to come up with your own mathematical relationship between the points, what type of graph do you think best fits the data? I mean, they drew a line there.
It's like a exponential.
It looks like a negative exponential, right? It looks like it's dying down like this, correct? Now, they did the best fit line and got an R value of negative 0.86. And negative 0.86 indicates, it indicates that it's very strong or a strong relationship, right? Just because your R is strong does not make, okay, Ashley, thank you. Just because your R is strong, or you get a value in a strong region, does not automatically make it linear. You still should check the data to decide whether or not linearity is appropriate for that problem. In this case, I look at the data and I would think that a curve is much better. And if you go on Excel or one of your spreadsheets that can do best fit lines and stuff like that, there are certainly, you'll see in the category of the best fit curves, linear, exponential, logarithmic, polynomial. There's all these different types that it can be. And your first job is to check, is it linear or not? And if it's not, what is it? And can I linearize it? And all that stuff. But just be aware of the fact, and this is important, that just because you get a strong or a high R value does not automatically mean it's linear. Okay, you should still look at the graph and decide. Does that make sense? Are there any questions on that? I hope it's okay. So let's turn now to the next one. Example, extrapolation. Okay, so we have a car data. Okay, so this is back to the example that we had last time. We have mileage on the x-axis versus selling price on the y-axis. We saw that as the mileage increases, the selling price goes down. That's to be expected. We also have a linear plot. I believe we got a negative 9 points or 0.9 something from the they don't list the R value here, but it was pretty strong. I forgot exactly what it was, but it was pretty strong. And they computed the best fit line, 10.82 minus 0.113x. So first, let's interpret the slope. We drop 0.113 for every one forward. That's what a negative 0.113 slope means. We go down 0.113 as we move forward 1. So for every one what? For every 1,000 miles, that's the units, the Y drops. What is Y? Thousands of dollars. It drops by 0.113 thousands of dollars. In other words, for every 1,000 miles, it drops by about $113 in selling price. That's what the slope seems to indicate. The Y-intercept is 10.82. That indicates that if X was 0, if it was a brand new car, that the selling price would be 10.82 thousand or $10,820. Okay, does that make sense? Yes, no, maybe so. I hope so. I'm getting silence.
Yeah.
I don't know what
sense.
silence means, so it's hard to expect. But here's the thing about the Y-intercept. It's way outside the data, right? The data is only from 18 to 35. Okay, so we can't predict reliably the selling price of a car with 0 miles on it. It's outside the data. Or how about 150,000 miles on it? If we go far enough, the graph crosses the x-axis and is now negative. Are you going to claim that once the mileage gets to a certain point, you pay someone to take it off your hands? Well, I don't think anyone would ever do that. You might give it away for free, but I don't think you'd pay anyone. So once again, once you're outside of your data, you have to be very careful because the best fit line only applies to the data and not necessarily beyond it. Okay, so that's just reiterating the same idea. And now 36, the very important association does not imply causation. In a study, one or more lurking variables may be present that have an impact on the response variable, explanatory variable, or both, but was not included among the variables studied. In other words, number of cars, studied. Age, studied. Income, that bridging variable that's lurking behind the scenes, was not studied, and possibly other lurking variables that we're not thinking of. Okay, when you have these other variables, they confuse the issue. They confound the issue because now you have so many things to worry about. Which one's really the cause? Or is it a combination that's really the cause? Well, how do you check? So there are statistical techniques that allow you to eliminate some variables and focus on others and do this and do that. We're not worrying about that right now. We're just conceptually talking about the idea of having confounding variables, okay? So what are some explanations for an observed association? One, the dotted lines show an association. The arrows, oh, I see, okay. So in these three pictures, Dotted lines show an association. So if there actually is causation, which is what the arrow is, if X causes Y, then obviously X and Y are associated with each other. They're connected. If Z causes both X and Y, then again, X and Y are associated, but not because one causes the other, just because they're connected through Z. So in that case, it's a common response from Z being the explanation. And then the last case is the confounding situation. Z causes Y, X causes Y, therefore X and Y are associated. But if you just analyze X and Y, you're ignoring the impact that Z has on Y, which can confound the mathematics and your analysis and your conclusions. Okay, so we have causation, X causes Y, that's a great situation, we love that. The left one, fantastic. Two variables, nothing else, this causes that, awesome. But if one thing causes two, they're connected, so there's a Z behind the scenes going on. And the worst case scenario is, yes, X causes Y, so X and Y are related, but Z also causes Y, and you're not taking that into account. In that case, it's confounding the issue. So sometimes you'll have a lurking variable that confounds, and sometimes you'll have a lurking variable that just explains both, but you always got to be careful about that. What do you do when there's a lurking variable? How do we account for that? A better statistician is one who has a better understanding of possible lurking variables, and that comes with experience. And then from that knowledge is able to design experiments that hopefully eliminate the possibility of that lurking variable having an effect. Okay, does that make sense so far? I hope so. Let's move on now to to slide number 37. It says a study of grade school children ages 6 to 11 found a high positive correlation between reading ability and shoe size. Do children with larger feet tend to read better? Do children with larger feet tend to read better? If you just look at foot size and reading ability, it shows that yes, children with larger feet tend to read better. Is there a reason, a common, a lurking variable as to why children with larger feet tend to read better?
Yes.
Age.
Yeah, because people with bigger feet are older, and people who are older have had more schooling, and therefore they tend to read better. So age gives a reason for both of these. It's a reason why the feet are bigger. It's a reason why the reading ability is bigger, and therefore those two things are associated, but not because one causes the other, because they're connected through age. The next one, over the past 10 years, there's been a high positive correlation between the number of South Dakota safety inspection stickers issued and the number of South Dakota traffic accidents. Do safety inspection stickers cause traffic accidents? No, I already gave the answer here. The bigger the population, the more accidents, and the more stickers are issued. So there's a lurking variable that explains both, which explains the association between them. So let's go to the next slide. It says, next slides are from the textbook, but needs a lot of cleaning and filtering. Thank you. I'm sorry you didn't do that. Whoever made these slides and gave them to me to use. So correlation does not imply causation. We already explained that. So let's go to here. Evidence of causation. Okay, so the question is, we know that just because you have correlation does not automatically imply causation. So the question is, well, how do you know if there is causation? Right? I mentioned common sense earlier, but are there things that we can develop into common sense? So if the association is strong, if it's consistent. Oh, this is going on the previous slide, so I guess we should talk about it. So even very strong correlations may not correspond to a real causal relationship, okay? Correlation may be explained by a lurking variable. So let's take a look at this. Social relationships and health. Does lack of social relationships cause people to become ill? And just so you know, there was a strong correlation. Lack of social relationships and people becoming ill. Or are unhealthy people less likely to establish and maintain social relationships? Does it go backwards? Do people who become ill often have a lack of social relationships? Or is there some other factor that predisposes people to have lower social activity and to become ill? So is there a lurking variable going on behind the scenes? So how do we know if it's causation? Well, we want the association to be strong. We want it to be consistent. I'm not understanding what this is talking about, this slide. Higher doses are associated with stronger responses? I'm not really following this slide, so let's ignore it because it's stupid. And let's go to the next one, right? I don't like stupid slides. So let's go to the next one. Cautions about correlation and regression. Again, correlation and regression linear lines describe only linear relationships. They are not resistant measures. What are some other not resistant measures? I forgot. Someone remind me, what are some other non-resistant measures? Things that are easily affected by outliers?
Mean.
Mean.
And the
standard deviation.
excellent mean and standard deviation. So like those, correlation is non-resistant. It says beware ecological correlation or correlation based on averages rather than individuals. Okay, so when you average things out and use those for correlation, you're not really using the actual data itself. And therefore you cannot trust it. Beware of extrapolation outside the range of data. Beware of lurking variables that either can confound the issue or are a common explanation. And again, always just remember, correlation does not imply causation, ever. I can skip this. Oh, I guess this is out of order. Okay, so are there any questions before we move on? Are there any questions so far? Someone did say the median, by the way, as a non-resistant measure, but remember the median is very resistant. Because if you make an outlier, the median will barely move because the median is just the middle term. So if you add one, the median will go up a little bit, but not very much. But if you add a big one, the mean will go up a lot. Does that make sense? I hope so. She who said median. All right, so let's look now at slide number 43. The residual. I already mentioned residuals in terms of the least squares best fit line. A residual is the difference between an observed value and the value that's predicted by the regression line, right? So if you have the line here, the dot above it, right? I think we did that last time. I'll just quickly annotate again. When you have your best fit line, you know, let's say you have 3 dots and you decide that that is the line that best fits. The difference between the data points and the line, that vertical distance is your residual. Now, if you're on top, it's a positive residual because the observed is greater than the predicted. And if you're on bottom, it's a negative residual because the observed is smaller than the predicted. The residuals represent the leftover variation after fitting the regression line. Okay? So you fit it as best you can, and the residuals are what's left over from being a perfect linear relationship, although I don't really like that term. But I think it's more conceptual. The mean of the least square residuals is always 0. If you add up the residuals and average them, you will always get 0. Some are above, some are beneath. If you add them up, you get 0, which is why we always square them first so that we don't have the cancellation that we have from the actual residuals. Now, sometimes you might want to make a residual plot. Okay, a residual plot is a scatter plot of the residuals against the explanatory variable. So if I look at the next slide here, this is the actual data right here. On the left is the actual data. This is slide 44. And you have lots of data points. There must be something like 20, 25 data points here, give or take, maybe more, I don't even know. And they draw the best line through them. What you'll notice is every one of those dots, I don't think there's a single one that actually falls on the line, which means every one of those dots has a residual. About half of them are positive residuals and half of them are negative residuals. So the second plot on the right is a plot of the residuals. So let's look, for example, let me share again so you can see what I'm doing. Let's look, for example, at, I'll go, okay, this one right there, that data point. What is the residual for that data point? Well, it's the difference, the vertical difference between the data point itself and the predicted, which is the best fit line. This is about what, 3,700?
Yeah.
Okay, 3,700. The line is about 2,800. So that looks like a residual of about what? 900? 900, right?
Oh, yeah, 900.
So we go here for the same X value. This is an X value of 325 or so. We should expect to have a 900 residual, and that's the residual for the same point. Right? It's the value is about 900. Does that make sense?
May you repeat the last part, please?
So what we're doing on the left is your actual data, and then we have the best fit line. Each data point has a residual. It's the distance between the point and the predicted, which is the line. On the right, we just plot the residuals. So if I go to this one here, its residual is about what, 300? Give or take, 300?
Yeah.
So if I go to the same X value, I expect to have a 300 residual. So the value here is just straight up 300. We actually plot the actual residuals on the right, as opposed to the data, which is why here the mean is 0, right? It's everything is centered about 0. The residuals always have a mean of 0, and some of them are positive and some of them are negative. Same X values, but rather than plotting 3,700, which is the actual data, we plot 900, which is its residual. Rather than plotting 3,100 or 3,200, we plot 300, which is the actual residual. So this is a residual plot. Okay, does that make sense? Again,
Yes.
not explaining why we're doing it, but let's go back one slide, back to slide 43. It says residual plots help us assess how well a regression line fits the data. Your goal is to look for a random scatter around 0. So if the residual plot is a random scatter around 0, then that's a residual plot that represents a good regression line. If it's not a random scatter, if there's a pattern to it, then that most probably represents a bad regression line. Let's take a look at the next slide. It says an observation is influential if removing it would markedly change the result of the calculation, because the results may be of little practical use if it depends strongly on a few influential observations. Outliers in either the X or Y direction are often influential, and outliers in the X direction are often influential for the least squares regression line. So something that influences strongly the mathematics, we call it influential observation. How do you know if it does or not? If its removal makes things markedly different. Let's look at the next slide to see an example.
I got a question.
Yeah, go ahead.
Does that mean that most information would fall under, I don't know how to really put it, but just not important outside of outliers, or?
I wouldn't say not important, but rather most of them kind of fit the pattern. So they're important in setting the pattern, but not so important to disrupt the pattern. Right? The influential observations disrupt the pattern caused by the other ones, but the other ones set the pattern. They're both important, but this one, I wouldn't say is more important, but the effect it has is one that markedly changes everything, as opposed to the other ones which just reinforce the pattern that you already expect.
I see.
Does that make sense?
Yeah.
So if you look at slide 46, you see subject 1 on the far right and subject 2 on the upper right. So if we include all of the data, then subject 2 has lifted our best fit line to create a positive correlation. Not strong, it's 0.181, it's extremely weak, but it's still a positive correlation. And then by removing subject 2 and not having that at all, the best fit line now shows a negative correlation. Still not that strong, negative 0.043, but still it's there. So subject 2 would be an influential observation because it changes drastically the nature of the correlation from positive to negative. None of the other points would have that effect. So subject 2 in this case would be an influential observation. Does that make sense? Seem reasonable?
Yeah.
Okay. Now, what if you want to study categorical variables that are also quantitative? Like, for example, the difference between ACT and SAT. So ACT and SAT, those are, of course, categorical. But their scores from SAT, or maybe not SAT and ACT, because those are different scales. Maybe we do SAT verbal, English versus SAT math. They're still categories, but let's say I want to look at their scores and see if there's a connection between their scores. So how do I do that? So if you look at slide 47, we see the relationship between mean SAT verbal scores and the percent of high school grads taking SAT for each state. Okay, so we have this scatter plot. Now, if I look at this data, if I ignore everything else, if I just look at this data alone, what relationship do I have here? Positive, negative, neither?
Negative?
Negative.
It looks like a negative relationship, right? But at the same time, it kind of seems that the ones on the left are clustered and the ones on the right are clustered, like two distinct groups. And because of the clustering, that's why I have this negative correlation. But maybe there's like a connection between these and a connection between those. And in fact, if you go to the next slide, it's the same data, just different scale. But if you go to the next slide, you see that the ones on the top left come from the Midwest states, and the ones on the bottom right come from the Northeast states. And if you did not include that categorical information, you'd just see this negative trend and really wouldn't understand a vital aspect of the data, that the red states, the Northeast states, tend to have a higher percent of students taking the SAT, and the blue states, the Midwest states, tend to have a lower percent taking the SAT. Why a lower percent? Because in the Midwest, the ACT is more predominant. Who are the ones who take the SAT in the Midwest? Those who probably also took the ACT and want to expand their recruitment across the country. probably the better students. And because they're the better students, that's probably why they took the SAT, and that's why their scores were so high. But we wouldn't have seen that had we not included the categorical nature of the information. And how do we include the categorical nature of the information? On a quantitative graph, we use different symbols: red, blue, boxes, circles, X's, circles. I mean, you do whatever you want, as long as it's easily discernible what your two categories are. Okay? Does that make sense in general, in theory? The ability to add categorical information to a scatter plot. Yes, no, maybe so?
Yes.
Okay. And the last slide, again, we don't need that. Examples of technology. The last slide just shows you that Crunchit can give you the best fit line. I'm pretty sure we did that already on Crunchit. Crunchit, this topic makes my brain hurt, someone said. Well, I wish I knew how to respond to that. You know, earlier, yeah, go ahead.
Do you think you could, wait, did you post the video where it shows how to use Crunchit?
I mean, it's always possible that I forgot to post my videos, but we did it in class, didn't we?
Yeah, all right, so never mind then. Thank you.
Yeah, I can show quick. I can just do it again quick for a random example. Let me load it up here.
Please.
Sorry?
Yes, please.
Yes, please. So I think we did this already. You put in data, you know, I gotta double click, hold on. You know, 1, 2, 3, 4, 5, and 12, and 12, and 14, and 11, and 8, and 17. So then you go to graphics, and you do a scatter plot. And you say X will be variable 1 and Y will be variable 2. And that's my scatter plot. Not a great scatter plot. Let's change my number here. Let's make it more linear. What's 1 would be 17 instead, and this one will be 12. Let's try that again. So
Oh, you just put in 112 rather than 12.
that would change things considerably. Thank you. So scatter plots. Okay, that's better. That's better. We'll probably have something that looks like this, cuts right across there. So what we're gonna do is we're gonna go to statistics, and we're gonna go to correlation first, and two variables, variable 1 and variable 2. I'm interested in what the correlation is. Negative 0.7526, which puts it where? Is that non-existent, weak, medium, or strong?
Strong.
Wrong.
I thought
Or like
strong
anything.
wasn't strong 0.8 or higher?
Isn't it weak?
No, definitely not weak.
Is it moderate?
Well, it's
Like-
in the border between moderate and strong. I think strong was 0.8 or higher. So it's moderate, but it's fairly strongly moderate, if I can make that up.
But it's negative. It doesn't matter if it's negative or
Well,
positive.
negative just tells us that it's going down versus up. The numerical values it's the same idea.
Okay, thank you.
Yeah, and then I go to regression, and it's simple linear, and we'll do two things. First, the dependent variable is variable 2, and independent is variable 1, and I want the numeric results. Numeric results tell me what the equation of my best fit line is. And then I will go back here and do regression again, and this time I don't want numerical results, I want a fitted plot. Okay, and then we have that. And you'll notice I also saw there that I can do a residual plots. And the residual plot is what we just studied, where you have your residuals. So Crunchit can do residual plots too. Isn't that amazing? Wow, I think it's amazing. But you guys, where am I going here? Crunchit, there we go. So here, this is Crunchit. It has these things that we're not ready for yet. So let's not worry about those, but it can certainly give you the linear regression line. That's what it does right here. And it gives you your R value. That's what this is right here, this correlation. And it does not give you the R squared value. How do I get the R squared value? how do I get the R squared value? Let's see what this is. Oh, that's something else. Oh, but this is interesting too. How do I get the R squared value?
Can't you just square that correlation value?
That's exactly what it is. You take your R and you square it. Now you have R squared. And none of the other things are appropriate right now. So I don't know where this output came from, but we'll get it eventually. Anyways, does that make sense?
Yes, thank you.
Yeah, so someone said this crunch it was worth the $90 just for the crunch it. It's pretty amazing. It's pretty amazing. Okay, so we just finished chapter 5, and the chapter 5 homework has been up, or should be up. How do I get back to? Hold
So
on.
does all the homeworks get pushed back?
You mean because someone wanted an extension?
Yes.
I don't think they should get pushed back. It's just I gave a little extra time because someone asked for it, but I wouldn't say it's pushed back. So everything else is still due when they're said. Now listen, if you run out of time and you need an extension, just ask. You know, I'm not against it. But the test will be next week. I'm just waiting to hear back from my professor. I told him that we are running a little behind because he already told us to put the test up. So I have to wait back to hear from him and him to say, no problem. You know, next week is good. But right now we have finished the first 5 chapters. Let's take a little break. Can we have a homework extension for chapter 4, please? What did I just say? If you ask for it, I'll give it to you, right? And she said, please. So, you know, no, I have to. So, wait, I already did homework 4 extension. I did it till Thursday. Yeah, that's already extended. And 5 will be due next week. And the next one we're going to do is chapter 8 because 1 through 5 and 8 are on this next test. So let's take a 5-minute break. I don't think I have PowerPoints for 8, which means I got to actually teach on my own, which is crazy. But luckily, I know what I'm doing. So let's take a 5-minute break, and then we'll come back and we will we'll continue. So take a little break. I need a drink anyways. I'm out of vodka anymore. Good stuff. Good stuff. Mm. Oh. Where is it? Do you have office hours after class? I do have office hours after class. You're more than welcome to stick around. All right, I can't find any notes for chapter 8. Okay, so we got to do it the good old-fashioned way. Hopefully everyone's back. Let's see. Are we going to do the exam on Canvas or Sapling, or just like doing the quiz last time? So it looks like the exam will be on Sapling because I just uploaded it on Sapling. So it'll be on Sapling. Okay, well, glad that answered that question. So we are doing now chapter 8. Chapter 8 is a small chapter. It is a non-mathematical chapter, which is always nice. And chapter 8 is about producing data. Okay? In fact, that is the name of the chapter, producing data. Where does the data come from? The data comes from sampling. Okay? You have a population. For example, what's on everyone's mind these days is the election. All right? What are we in September now? So about a month and a half away, and we're going to have an election. And people are extremely divided. I'm not saying it's 50-50. I'm just saying I've met very few people that are like, whatever. People are very strongly opinionated on one side or the other. So it's a hot topic. So people are interested in predicting who's going to win the election. Now, if I can somehow poll every single person in America and ask them who they're going to vote for, every voting age, then, and assuming that they were honest, then I would know the answer. Assuming that there's no votes lost, or there's no computer malfunctions, and all those things that actually do happen in the real world, I would have the answer. But of course, I can't do that. I don't have the time, I don't have the money and the resources. So how do I get an accurate guesstimate of the actual outcome in practice? I take a sample. I look at a small segment of the population, and I ask them, and I take the results of that sample, and I try to apply those results to the entire population. So if you have the book in front of you, on page 192, in bold print are 3 definitions: the population, the sample, and the sampling design. Now the population, I'm reading it word for word. The population in a statistical study is the entire group of individuals about which we want information. It says, give me a second to load it, please. Go ahead. You should have the ebook on Sapling or the actual textbook. Either way, we're on page at least 192 of my version. Does anyone have the book in front of them? I want to make sure that we're looking at the same thing.
I have it in front of me. I don't think it's 192.
What do you have on page 192?
Chapter 7 is saying pure tone response.
Okay, hold on. What's chapter 7 called in your book?
Exploring data, part 1. Review. Oh, or test yourself.
Okay, okay. So go to chapter 8. Maybe you have a different edition than I do. What's your chapter 8 called? Actually, you know what? Hold on a second. So I have the hardcover, and then I have this that they gave me this semester. It looks to be the same. Let me open this. Yeah, it does come with the Sapling account. There's an ebook. I think there's an ebook. There should be. Let's find it. Go to Sapling. Let's make sure we all have access to this. This is very important. So let me load up my sampling account. Okay, so I'm in my course. On the right, it says e-textbook. Do you see on the home page on the right, it says e-textbook? No? Hold on, I'm gonna share my screen. So when I share my screen, this is my homepage, Math 140, my name, this over here on the right side, e-textbook, the basic practice of statistics. If I click on it, to begin, enter your email. Let's see, which one is it?
You can skip it.
You can just hit finish.
On the last page that you were on, it said you can just skip it.
Oh, okay, 1 second. And here we go. Is this, and there's some tables.
On the left side, the search.
Oh,
You
I
can
see.
just
Oh, there we go. I was covering it up. So table of contents. We will go to chapter, we go to part 2, producing data. And that's where I am. Okay, so that's the exact page. In this thing that they gave me, let's turn to the right page, and it is page number 192. So I have 192 in both this book and in my hardcover. But you know what? Since I'll just be reading from the book anyway, I'll just keep it up here so you can all see it. Although I did see someone, someone texted. How do I? Hold on. Could you share? Found it. Okay, producing data. Okay, so back there. Okay. So we can all see this population versus sample.
yeah.
So a population is a study of the entire group of individuals about which we want information, whereas a sample is part of the population from which we actually collect the information. And then we use a sample to draw conclusions about the entire population. This is the core of statistics, okay? And a sampling design describes exactly how you're gonna choose a sample from the population. There's multiple ways of choosing your sample. As we're gonna see in 8.2, how to sample badly. And then we're gonna have other sections of different types of samples, okay? But right now, 3 things. Population is everyone. The sample, that's the part that you get. And the sampling design is your approach to how you got your sample. Did you do a cluster? Did you do a stratified sample? Did you do a simple random sample? Did you do a convenience sample? Did you do a voluntary response sample? Did you do a survey? Did you do a poll? Did you do a this? Did you do a that? Your method for choosing your sample is called your sampling design. Some of them are good, some of them are bad, as we're gonna see. Okay, so 8.2, how to sample badly. Okay, so how can we choose a sample that we can trust to represent the population? Okay, that's, the method that we're gonna do it is going to be the sampling design, but the question still becomes, how do you go ahead and do it? The worst possible thing you can do, not the worst, but one of the worst, is called a convenience sample. A convenience sample is just a sampling that's convenient. I'm going to go outside my house and just ask the first 100 people who walk by. It's convenient. It's quick. I don't got to do much work. They're all there. Why is that a bad sample to represent everyone? Well, maybe because wherever you live is a demographic that has voters of a certain type. Maybe it's this nationality. Maybe it's this political affiliation. Maybe it's this, whatever the case may be. But you want to have a sample that's representative of the entire population, and convenience samples usually miss that because you're not taking into account being careful about it. Okay? You're just asking whatever's the most convenient. Oh, yeah, I'm curious. I'm going to go to everyone in my school. Well, your school has lots of 20-year-olds. And 20-year-olds are in many ways very similar. And again, do not necessarily represent everybody. And as such, it's not representative of the population. It can have some bias to it. Bias is when you have a design that favors certain outcomes over others. Here's an example. I'm curious what everyone's favorite sport is in America. So I'm going to take a sample. I'm going to ask 1,000 people what their favorite sport is. Now that's 1,000, it's a lot of people. That seems like it's a pretty good sample size. So how am I going to do it? Well, you know, I have tickets to the Lakers game tomorrow night. So I'm just going to go to the Lakers game. And when I'm there, I'm going to ask 1,000 people randomly. Randomly, that's good. I'm going to ask 1,000 people randomly what their favorite sport is. Does that seem like it's a reliable sample for what I'm after? Or does that possibly have some bias to it? Yes?
Yes.
It's good or it's bad? Oh, I have some text. Oh, how do I get it? Oh, there we go. Texts, chats. Okay, strong bias, not reliable. Okay, bad. Good. People were saying very biased, right? So why is it biased? What's in it? Just because you go to the Lakers game doesn't mean you love basketball. It's just the fact that you're probably more inclined to like basketball if you're at a Lakers game. So therefore, it systematically favors basketball as being your favorite sport over something else, and therefore it is not a good sample. It's convenient. I'm there anyway. I'll just ask 1,000 people, but it's not designed in a way to eliminate bias. That's a bad sample. Does that make sense? Another bad sample, a voluntary response sample. A voluntary response sample are people who respond if they want to. What's an example of a voluntary response sample? You ever online come across some kind of poll on a website? Like, what's your favorite Game of Thrones character? What's your favorite this? What's your favorite that? Who are the people who answer those kind of questions? People who are very much involved in that particular subject. Whereas everyone else will just skim over it and say, I don't have the time for this. Right? So voluntary response people is biased because it's for people who have very strong opinions about that particular subject. And that might not necessarily represent the average person. At the end of a customer service call, they ask you to take a survey, right? I never do that. I don't have the time for that crap. And even if I did, I just don't want to. Who are the people who will? People who are very strongly opinionated. Yes, this is horrible, or yes, this is awesome. You don't have any, people like that don't take, a census is different. No, a census is very different. Someone said a census. A census is amazing because a census, they literally ask every single person. When America does a census every 10 years, they go to every single household in America to get an idea of the population. Now, are they missing people? Yes. There's homeless people. There are situations that are unfortunately out of their control. But censuses are exactly the opposite. For censuses, it's not a sample. It's pretty much the entire population. We'll get to that in a few minutes. But right now, we have two bad types of samples. We have convenience samples, and we have voluntary response samples. Those are bad. Okay? Don't do them. The best type of sample, as a general rule, is a simple random sample, an SRS. We will use the term SRS throughout the entire semester. Okay? Most of the formulas that we come up with from here on out are going to be given an SRS, and then here's the formula. So we will assume, for the most part, that we're dealing with a simple random sample. So what is a simple random sample? Well, one, it's a sample. So you're getting a portion of the entire population. You're not getting everyone. Two, it's random, but it's random in a very specific way. Imagine if you were, for a second, in a classroom of 50 people. You have 50 students in a classroom. So just imagine you're the teacher and you have a class of 50 students, and you decide that you are randomly going to pick 5 of them. Sure, you could put everyone's name in a hat and pick them out, which is awesome. That's an amazing way of picking 5 randomly. But suppose you didn't have the time for that. Suppose you just say, I'm just going to pick 5 people randomly. What would you do in that situation? Practically, what would you do if you are trying to pick 5 people randomly from a class of 50 students? What would you do? Quick, you have, first 5 to raise their hands is not random. Because then people who are very much motivated, want the extra credit, care about it, are people who will be the first to raise their hand, right? So I heard 2 great answers. One, someone said, whichever my eye catches. And the other one says, if it's an actual classroom, 1 student from every row. Then someone said, close my eyes, spin around and point. I kind of like that one, actually. Okay, I like that one. So I already said the names in the hat is wonderful. So every 5th in the roll call. Okay, so these are some great answers because a lot of them are wrong. And it's wonderful to have wrong answers because it shows us that our understanding is wrong. And that's how we learn. So 1, whichever my eye catches, that is not random, okay? That is the opposite of random. That's specific. Like, oh, him, I made eye contact with her. I like his hat. He's just weird. Whatever the case may be, that is not random. That's very specific. Someone said every 5th in the roll call. That is as opposite as random as you can get because every 5th in the roll call is very systematic. Very systematic. The 5th, the 10th, the 15th, that's very systematic. There's no randomness at all to that one. Okay. Who has black shoes? Is that random? Everyone above 20 plus war zone wins. I got to play this game because I have no idea what we're talking about. But the one that I want to focus on, someone said he said, 1 student from every row. And this is, I think, the way people would think they're doing it randomly. They would say, let me pick 1 from this area, 1 from this area, 1 from here, 1 from here, and 1 from here. But that is not random. I mean, it's semi-random. But you would never get 2 people next to each other if you did it that way, right? If we picked 2 people next to each other, our mind would say that's not random. But if you really put the names in a hat, like some people recommended and pulled it out, is it possible that you get 5 people in the same row? It's possible, right? But if you did that on your own, people would say, that's not random. You just picked that row. A simple random sample is one for which any possible sample is as equally likely as any other one. So if I'm picking 5 people out of my class of 50, every possible group of 5 people is as equally likely as any other group of 5 people. You will not get that picking what you think is randomly because there's no way that there's any chance in the world that you'd end up with 5 people in the same row. Human beings can't do that. Names in a hat, that can do it. That can be random. Making a random number generator, giving a number to each person and having the computer do it, that can be random. But human beings cannot be random. So a simple random sample of size n is n individuals chosen from the population in such a way that every group of n people is as equally likely to be picked as any other. That is what a simple random sample is. And it is the best kind of sample, and is the one that 99% of the time is the one you're going to want to use. There are times that other ones are better, but for the most part, these are the ones that we want. Simple random samples. If you look down a little bit, random digits, well, you can use a random number generator. Basically, you just have digits randomly. Like, do they have an example? They don't have an example. That's great. But suppose I just had a book that's full of just numbers here, for example. Suppose it says table B. Google has one. Yeah, Google has one if I want to show. Okay, so Google. Random number table. Right, so a random number table is just tons and tons of numbers. Okay, just randomly generated by a computer. Tons and tons of numbers. And essentially what I would do, if I had 50 people in the class, for example, is I would assign everyone a number from 1 to 50. And then I would pick the first 5. So let's say 80, not in my class. 94, not in my class. 25, okay, 25 goes. 25, already picked him. 82, not in my class. 47, okay, you go. 13, you go. 47 already picked. 74, not in my class. 33, you go. And 36, you go. So those 5 people, person number 25, 47, 13, 33, and 36. Those 5 people would go if I happen to use the first line. If I use the 6th line, 44 goes. I have no 90. I have no 54. 17. I have no 97. 27. 61. 53. 59. 81. I can't even read it because it's too fuzzy. But hopefully you get the idea of how to use a random number table to pick people randomly. Where's my book? Okay, so a table of random digits is a long string of 0 through 9 with 2 properties. Each entry in the table is equally likely to be any one of them, and the entries are independent of each other. What I can do is I can assign people numbers and just go down the line and get them all. You don't got to do it by hands. You can do it on a computer, or usually every semester I give away a textbook that I used the previous semester because they always give me a new one every semester. We didn't meet this semester, so I wasn't able to do that. But the way we would normally do it is I would just assign everyone who wanted a number, 1 through 20, and then have my computer pick a random number from 1 to 20, and whoever gets it, gets it. So simple random samples are great, and random number generators can really do that for us. Okay? Now, at the end of the day, the goal is to go from your sample and infer something about the population. We want to go from our sample and infer something about the population. That is the goal of the problem. This is what pretty much the entire rest of the semester is about. How can I take information about my sample and infer something about the population? Okay. This was a very small section because basically it's just conceptually. Okay. The first reason to rely on random sampling is to eliminate bias in selecting samples. The reason why we do random sampling is because it helps us eliminate bias. The second is that the laws of probability allow us trustworthy inference about the population. We will need to take a detour into probability because it's only when you know probability that you can do statistics. Because if you have an outcome, you have to ask yourself, how likely is this outcome? Is it what I expect or what I don't expect? And the laws of probability will tell us how likely it is. And in general, larger samples give more accurate results than smaller samples. So at any time, if you are uncertain how large of a sample to take, go larger, okay? The larger it is, the more confident you can be that your sample is inferring something accurately about the population, okay? Does that make sense so far? Are there any questions?
Makes sense.
Okay. Now, what are some other sampling designs? So there's something called a stratified random sample, okay? A stratified random sample is you divide the population into groups called strata, and then you choose an SRS from each one. What's an example? Suppose I want to first divide up the population into males and females, so I can take a random sample of each one, because I expect the male and females for this particular experiment to be different. So I divide them. I can divide by state. I can divide by age. I can divide by, I can divide by anything. Okay, as long as I believe that each of those groups have similar characteristics, I can divide by strata, by groups, and then take an SRS from each one, as opposed to one SRS from the entire population. Why is it better that way? Well, suppose I pick a sample of 1,000 people from America. If I didn't divide by state, then it's theoretically possible that everyone that I pick is from California. I can get really unlucky that way and get everyone in one state. And that might not be representative of the entire population. But if I take 20 from each state and then do a simple random sample of each one, then it might be more representative. Of course, then certain states have lower populations than others. So there's ways of adapting this to have the population or the sample size from each one be proportional to the population of the state. Does anyone know in politics something that is proportional to the population of the state?
House representative.
House representatives, right? We know the Senate, you get 2 each, but the House of Representatives is proportional to the population, so this is not unprecedented. But a stratified random sample is when you divide it into pieces and take a SRS from each piece. Something similar to that, which I don't see here. I don't see it here, but there's something called a cluster sample. A cluster sample is the same thing. I divide it into pieces, but rather taking a small amount of each piece, I take a certain number of pieces in their entirety. So I might divide it into 20 pieces and take 3 of those pieces in their entirety, as opposed to 20 pieces and taking a small part of each of those pieces. A difference between a stratified sample and a cluster sample, but I just don't see cluster here. So that's kind of strange, okay? And usually you're gonna have multi-stage samples where, for example, you choose a random sample of telephone numbers stratified by region of the country, then an SRS of telephone numbers within each strata, and then a random adult in each household. So you can structure your samples in stages called a multi-stage sample. Again, very qualitative, not very mathematical. These are all just different sampling designs. So 8.6, cautions about sample surveys. So when you do a survey, there's 2 things you have to be very worried about. One is under coverage, and this is not just for surveys, this is samples in general. Is that someone typing? I can't see. Okay, so under coverage is when you don't represent the entire population. Some groups in the population are left out of the process of choosing the sample. An example would be if I do make telephone calls and I ask to speak to a person in every household, and suppose magically everyone says, oh yeah, I have the time to talk to you, I'm more than happy to. You're still missing a large segment of the population, which is everyone who does not have a house, doesn't have a home or a phone in their house. I personally don't have a phone in my house. I have my cell phone. I don't have a house phone. I mean, who has a house phone anymore? You don't need it. Growing up, we didn't have cell phones. You had to have a house phone. Nowadays, you know, it's not really that important. So you might have under coverage. You might not cover everyone. And then, of course, there's non-response. That's when you did find someone, but either they can't be contacted or they refuse to participate. They just say, I don't have time for this nonsense. All right, ask someone else. I mean, who really wants to sit there and take their time to answer a survey? Okay, I mean, it's just boring. So these are 2 concerns, because if you do get non-response, you're gonna have bias. The people who do respond are people who are very much enthusiastic about the subject. That's not representative of everyone, right? So there's 2 reasons why you'd have bias. 1, you missed out on some people, and 2, the people who do respond are the ones who are very invested, and again, the ones who don't might have given you a completely different result. Okay, does that make sense? Any questions so far? I don't know what this is. Someone writing something? I can't tell. Okay. I'm going to move this for a second because there's some. Oh, that's nothing. Okay. And then finally, we have 8.7, the impact of technology. You know, nowadays, you don't even have to do a survey anymore. You can have an automated survey done for you. You know, there's web surveys on the internet. You don't got to talk to anyone anymore. So I'm not sure exactly what this section would add to your understanding. So if you want to read it, go ahead, but I can't really imagine a scenario where anything in this section would ever be asked on a test. I mean, it's one page. I recommend reading it, but essentially all it's saying is that with modern technology, a lot of these fears are even bigger because you have the internet and people on the internet don't have time, so they'll only respond to what they care about. So you'll have the same issue that we had before of under coverage or or a voluntary response. And you know, cell phones, you can't call cell phones anymore because people block all these telemarketers. So anywho, very small chapter, but included on the test that we're going to have next week. So as soon as I hear back from my professor, let's see, I have 3 emails. Did he responds? He did not respond yet. So as soon as I hear back from my professor, we will have a more specific timeline for when the test is going to be. But for now, we have finished the first 5 chapters and chapter 8. Chapter 4 homework was pushed off till Thursday, but 5 and 8 will be due sometime next week, probably next Thursday. Are there any questions on anything? You are welcome. Relatively straightforward, I thought, today. Very conceptual, not very mathematical. This chapter, we do know the exact definitions. Well, it's an open book test, so you know you can always look at the definitions if you need them, but it's really more the concepts that you should understand. I know the general ideas, but if you have to look something up, have your textbook available to do that. Okay, I'm going to get something to eat and drink because I've been working for the last 10 hours. So unless there's any questions, you guys are free to go. I'm going to stop recording now.